Okay. This next lesson is designed to be a very brief introduction to correlation and then, more importantly, to linear regression. Okay. Um, Linear regression itself is the foundation of uh, econometrics. And so if the viewer likes linear regression or wants to know more about it, then the most appropriate direction to head in would be to start studying econometrics. Okay, so let's start with correlation. Just do some basics of correlation, and then we're going to start talking about linear regression. Okay, so correlation. Correlation is a measure. It's something, it's a numerical indicator. Let's put it that way. It's a numerical that measures the strength of the relationship between two variables. Okay. It's a numerical indicator, numerical measure, right? It's a number that measures the strength of the relationship between two variables. Now, there could be positive correlations, there could be negative correlations, there could be no correlation. In fact, there could even be something called a spurious correlation. Now, I'm sure that you have probably heard and used the word correlation before in your life, right? You've heard people say like, "Oh, those two things seem to be correlated," or they're these things are correlated with one another, something to that effect, right? Well, what are they actually saying? Okay, what they're saying when you talk about correlation, you're just talking about a numerical indicator. You're talking about something that measures the strength of the relationship between two variables. Importantly, okay, note when there is correlation, it is not measuring or identifying causality. There is no causality here. We are just simply measuring the strength of the relationship between two variables. Okay. So, what is a positive correlation? Uh, Usually it would be something like, let's say, coffee and cream. Okay. People usually like to drink some sort of cream in their coffee, whatever. So there is a positive correlation there. Since people like to, drink cream with their coffee or sugar or a donut or something like that, the two things seem to be correlated, right? Spaghetti and meatballs, right? These things tend to go together, right? There's a positive correlation. As one goes up, the other goes up. So as the consumption of coffee goes up, the consumption of cream goes up. As uh, as people eat more spaghetti, they need They tend to want to eat more meatballs. And, you know, things like that, right? A positive correlation, two things that tend to seem to go together. Okay, that would be a positive correlation. When one goes up, the other goes up. A negative correlation is just the opposite. Okay, a negative correlation would be as one thing goes up, the other thing goes down. Okay, so, or as one thing goes down, the other thing goes up. Okay, we know this in economics as the law of demand. Okay, there seems to be a correlation in economics that when price goes down, quantity demanded goes up. Okay, now that's causality, right? But there's also a negative correlation between, let's say, the temperature and the amount of bathing suits that people buy, right? As the temperature goes down, people are going to, or sorry, winter coats, right? So as the temperature goes down, people end up buying more winter coats, things like that, right? So there's a negative correlation there. Temperature go down, winter coat go up, okay? And vice versa, right? As the temperature goes up, winter coats go down. No correlation just simply means that there's no real relationship we seem to be able to establish here, okay? We can't really pick out any sort of discernible relationship. Maybe we could have hair color, right? Hair color and average salary. Okay. In other words, do people with black hair tend to have higher salaries than people with brown hair? And then people with blonde hair make the most, right? Would there tend to be, you know, a relationship between hair color and average salary? Maybe there's a slight one, but we wouldn't really expect to see, you know, a big correlation there, right? To say like, oh, well, it's this hair color that leads to this salary. You wouldn't expect to see a big correlation there. And then a spurious correlation is interesting. A spurious is what we might consider to be just a coincidence. Okay. A spurious correlation occurs when you think there is a relationship between two things. Okay. So it could appear, you could have a correlation appear to be positive, appear to be negative, or none at all. Spurious correlation, we could say this. Okay. So as it turns out, the number of asylum inmates tends to go up every year, and every year, so do professor salaries. Okay. So, in other words, every year professor salaries tend to increase, but then again, every year the number of inmates in an asylum tend to increase. Huh. So, there would appear to be a positive correlation there. Okay, there would appear to be a fairly strong relationship between paying professors more and the number of people who end up in an asylum. Okay, so the natural question might be, well, if we're going to pay professors more, does that mean that some of them end up in an asylum? Or do more people ending up in asylum mean that we're paying professors more? Right? What's the correlation here? What's going on here? Well, the answer is it's nothing's going on here, right? These two things look to have a positive correlation, right? There appears to be a positive relationship here, right? The numerical indicator, right? If you calculated correlation, the numerical indicator would come back positive. But at the same time, can you make any sense of it, right? Does it make any sense to you that, oh, well, as there's more people in an asylum every year and professor salaries go up every year, so therefore there must be a strong relationship between the two. That doesn't make any sense, right? So spurious correlations are just what we know of as coincidences, right? Like it looks to be a positive relationship. It could also look to be a negative relationship, right? It looks to be a relationship there, but we just can't make any sense of it. It just so happens to be a coincidence, right? That's a spurious correlation. But again, the thing about correlation is that it does not introduce causality. Okay, correlation is not causality. Just because there is a relationship between two things, we don't know what direction that causality is, right? In other words, is it people drinking more coffee that leads to more cream? Or is it more cream that leads to more coffee? Okay. Well, obviously, it's the first one, right? It's people drinking more coffee, which leads to more cream, right? You don't generally see a lot of people drinking cream and then saying, like, you know what, this would go great with coffee. No. But you do see plenty of people having coffee saying, I need a little bit of cream in this. Okay. But at the same time, let's talk about spaghetti and meatballs. Spaghetti and meatballs tend to have a strong positive correlation, right? One goes up, the other goes up. But is it the spaghetti that makes you say, you know what, we should have meatballs with this? Or is it having the meatballs that say, man, this would go great with a plate of spaghetti? Okay. Now, you could probably see an argument both ways. You could say, oh, well, people want spaghetti, they're going to want meatballs. Well, if people have meatballs, they're going to want spaghetti. So both lead to each other. And that's exactly my point. That's a correlation. There's a strong relationship between the two, but we don't necessarily know the causality in that relationship. The causality, the whole importance of that, that's where linear regression comes in. Okay, linear regression. That's why linear regression is so important. Linear regression introduces causality. Okay. Linear regression is the ongoing process of establishing the size and direction of a causal relationship between an independent and a dependent variable. Okay. It's an ongoing process of establishing the size and direction of a causal relationship between an independent and a dependent variable. Okay. What do I mean by that? Well, let's think of a relationship that we know quite well at in higher education, right? Why do people tend to want to get college degrees? Well, you want to get smart, right? In other words, why do people go to college? Well, you want to get an education, you want to become smarter, right? You want to get training for on-the-job experience. And all these things tend to be related to you wanting to have a high salary in your life. In other words, people go to college and get specialized training in their majors because they want to end up having higher salary jobs than individuals who only have a high school education. Okay. So, in other words, what we're saying, we're establishing a relationship here. We are establishing the belief that there's an independent variable, years of education, right? People can decide to drop out of high school. They can finish high school. They can get an associate's degree from a community college. They can get a bachelor's degree from an undergraduate institution, just like ours. You can get a master's degree. You can get a doctoral degree. You can get a postdoctoral position degree. Okay. You can even get multiple PhDs. So all of these things, those are independent decisions, right? When you finish high school, you can decide, you know what? That's it. That's good for me. I'm going to go into the trades. I'm going to become an electrician, and that's that. Or you could decide to become a physics major, get a PhD in physics, and then become an astronaut. Okay? You can decide to do those things. Those are independent variables. You make the choice of how much education you want to get. However, most people go to college because they recognize that their choice of how many years of education they have, that independent variable highly impacts what their income level will be for the rest of their life. Okay? So let's talk about linear regression. Linear regression is the ongoing process. Ongoing, it means that you have to continually look at your model. Okay? It's the ongoing process. A process is something that happens through time and over time. It means a process is something that's usually ongoing, or it takes time. It's the ongoing process of establishing, you are establishing the size and direction. So in other words, the size. How much does this thing impact this thing? Is it a lot? Is it a little? Is it an enormous amount? Is it not at all? How much does this thing impact this thing? We are going to look at how to figure out the size and the direction, right? Direction just means when one goes up, the other goes down. Or when one goes up, does the other go up? If one goes down, does the other go down? So we're looking at the size, how much one impacts the other, and the direction. If one goes up, does the other go down? Vice versa. We're looking at the direction of causality, right? We're going to look at the causal relationship. We're looking at causality. In other words, how much does this independent variable impact a dependent variable? Okay, so in other words, when people decide to go to college, when they get more education, what is the size of that effect? Okay, when people get more education, well, let's start with the direction actually, right? When people get more education, when people go to college, does their income go up or down, right? More education, more income. Does it go up or down? Well, everybody, the Federal Reserve once again established this year with the 900th year in a row. Not really, but I'm being facetious. But once again this year, the Federal Reserve established that the most surefire way to reserve your ticket in the middle class and possibly the upper middle class is through a college education. So in other words, the Federal Reserve looks at all kinds of factors that determine your income level. And for the long time in a row, right? I think it was like the 47th year in a row. The biggest predictor of whether or not somebody is in the middle class is whether or not they have a college education. Okay. So what that's saying is that the direction of the relationship between the independent and the dependent variable, the direction of that is positive. One goes up, the other goes up. You get more education, you get more income. If you get a high school diploma, you get more income than a dropout. If you get a college, if you get an associate's degree, you get more education than a high school diploma. If you get an undergraduate degree, you get more income than an associate's. You get a master's, you get more income than an undergraduate degree. You get a doctorate, you get more income than someone with a master's degree. Okay, so in other words, the direction was positive. There was not an inverse relationship. And then the second thing to do is to establish the size of it. Okay, what it means by size is, all right, when one goes up, how much does the other go up by? Because what we're going to try to do here is it's the ongoing process of establishing the size and direction of the relationship between an independent and a dependent variable. In other words, what we want to do is we want to find out, okay, if I go to college and I get a master's degree, right? If I enter into graduate school, how much can I expect my income to go up by? Okay, the first thing is more education, income go up. All right, so that's the direction. We think if one goes up, the other goes up. Now I want to know how much more I can expect. Can I expect $2,000? Can I expect $45,000? Can I expect $15,000? Okay, that's what the size is. We are going to estimate the size of the causal relationship between an independent variable and a dependent variable. Okay. In other words, we're going to start making a model between income. So we'll say that income is equal to education. Okay. We'll do years of education. Okay. So how do we establish that relationship, right? Where do I find what the size and the direction of that causal relationship is? How do I get that? How do I find, in other words, if I get one more year of education here, right? If I do +1 for education, how much will this go up? And that's what I need to figure out. That's what I'm going to do here. And the way that we do that, the way you find out what that relationship is first you get data. You would get data on as many people as you could get your hands on. And you would get data on their level of income and how many years of education they have. Okay. And then what you would do is effectively you would graph it. You would put it into a computer, and then you would ask the computer to do something called the least squares principle. Okay, the least squares principle, which is what we're going to discuss now. Okay. Probably going to need a big graph for this. Let's say I have education on my horizontal axis, and then I have income on my vertical axis. Okay, so in other words, the X leads to the Y, right? I have education on the horizontal, income on the vertical. All right. Now, let's say that I have three people. I go out, I try to get data on as many people as I can. I find three people. I find Anna, I find Billy, and I find, I don't know, whatever, Dan. Okay. Now, what I want to do, I want to find out what is the impact that years of education has on income. Okay. I want to know, I want to establish, right? I want to establish a quantitative relationship there. Establish a quantitative relationship between years of education and income. Okay. How do I do that? In other words, I want to find out if I go to college for 1 year or for 4 years for undergraduate, how much is that going to raise my income by? All right. The way to do that is through this concept called the least squares principle. Okay. What the least squares principle does is it basically just, if you do this in a computer, right? Because you have to do it in a computer. You could do it by hand, but it would take you a long time. Okay. What you do is this least squares principle will find this lot, will find, it'll look at these points of Anna, Dan, and Billy. Okay. So Billy has this much education and he makes this much income. Anna has this much education, but makes this much income. Okay, so in other words, Billy has more education than Anna. Anna's education is here. She may only have a high school degree. Billy has a college degree. He has more education, but Anna actually makes more income than Billy does. Okay. Dan, on the other hand, Dan has the most education. Okay. Dan has the most education out of everyone, and he has the most income. He has higher income than Anna and than Billy. Okay. So what does the least the least squares principle do? Okay. The least squares principle is how we actually find numbers for our quantitative relationship. The least squares principle is how we actually find, oh, if you get a college degree, this will go up by $20,000 a year. But if you get a master's degree, this will also go up by another $15,000 per year. Okay? That's how we find it. And the least squares principle, what it does is it takes this graph, the least squares principle, and it shoots out a series of lines. I'm only going to draw two of them just to highlight the point. Oops, I don't even want to go that far. I want to go. Okay. So the least squares principle, if you type into the computer, do a linear regression, run the least squares principle. The least squares principle means that you are telling the computer to minimize You want to minimize the sum of squared differences between the actual values and the predicted values y hat of y. Okay? What does that mean? It means that you are going to minimize let me rephrase that. The least squares principle does is it tells the computer to choose the option, tells the computer to choose the option of the line that minimizes the distance between the actual values of the y variable and the predicted values of y. Okay? So what is that saying to us? All right, this is what it's saying. If you say, you know what, I want to run a regression, and you put this data into a computer the way that you will in an econometrics class. Okay, so you put data into the computer, you collect information on Anna, Dan, and Billy. You find out their education levels, you find out their income levels. And then you say, all right, you know what? Go. I want this to run a linear regression. How are we going to get the linear regression? We're going to do the least squares principle. Well, what's the least squares principle? In the least squares principle, we're going to shoot out two lines. This one, we'll call it line 1. And we'll shoot this one out called line 2. Okay. Now, what the least squares principle is doing, the least squares principle tells the computer to choose the line option, choose the option of the line. So are we going to choose line 1 or line 2? Choose the line that minimizes the distance between the actual value of y, the actual values of y. So this is Anna's actual value of y. This is Dan's actual value of y. This is Billy's actual value of y. So choose the distance between the actual value of the y variable and the predicted values of y. Okay? That's what it's saying. And the predicted values. So what do we mean by predicted values? We'll get to that real quick. But what the whole concept of the least squares principle is doing, it's telling the computer that, hey, I want you to give me information about the line that best fits through all of our data points. Okay? I want the line that fits through our data points the best. Okay? What's the line that fits through our data points the best? The one that fits through our data points the best is line 1, right? Line 2 is out here going like this, right? Line 1 cuts through the data, cuts through Anna, cuts through Dan, cuts through Billy. It actually goes through our data points. Line 2 is below all of them. Okay, so I'm making this a little dramatic to highlight, the logic behind it. But you may have heard of this before. It's called the line of best fit. And that's what we're doing here. We are trying to find the line of best fit. We want the line that goes through our data the most. Now, again, we're not going to calculate this by hand. We're having a computer do this, right? All we're doing is highlighting columns and then, clicking enter, telling the computer, do least squares, do linear regression, go, right? And then the computer goes, boo, boo, and makes all these and tells us the information we want, okay? But so here we have line 1 and we have line 2 here. Okay. Right here on line 1, these are predicted values. According to line 1, based upon Anna's education, she should have this level of income. Okay, based upon this level of education, the computer believes Anna should have this level of income. Well, she actually has this level of income. So she's doing better than the computer thinks she should be. Okay. On the other hand, Billy has this level of education. Based upon that information, the computer thinks that Billy should have this level of income. But in reality, Billy has down here. So Billy is doing less well than the computer thinks he should be. Right? Finally, based upon this level of education, right, the computer estimates that Dan should have this income level, but he's actually doing up here. He has that much yearly income instead. Okay. So what I'm getting at, and what's really important to understand linear regression, is that there are actual values of what the variable has. The actual value is how much income each person is making per year. And then the predicted value is basically just the line saying, all right, well, given that this person has this level of income, this level of education, how much would I expect the person to make? This is the predicted values, okay? The values that are on the line are the predicted values. The data points that are just out here floating, right, our data set, those are the actual data points. That's how much money Billy, Dan, and Anna actually are making every single year. Okay. That's how they're actually doing. I'm just erasing it to make it a little neater. Okay. So what the least squares principle does is it tells the computer to choose the option of the line, choose the line option that has the smallest gap, the smallest distance between the actual values. These are the actual values. Dan, Anna, Billy. Those are the actual values. So pick the line that has the smallest distance between the actual values and the predicted values, which are on the line. Once you have the line that has the smallest distance between the actual values and the predicted values, then you end up with the line of best fit. Okay, so let's see how that works. Well, here we have an actual value of Anna and we have a predicted value of Anna. Here we have an actual value of income for Dan and we have a predicted value for Dan. And then we have an actual value of income for Billy, right? He actually has this amount of money. And we have a predicted value, okay? Now, that's for line 1. Let's say that the summation, I'm just making these numbers up. Summation of line 1. let's say that this gap is 5, this gap is 5, and this gap is 4. Okay? Let's just say that there's 5 spaces between Dan's actual and predicted. Let's say that there's 4 spaces between Anna's actual and predicted. And let's say that there's 5 spaces between Billy's actual and predicted. Okay? So the summation, I'll just call it the total sum of line 1, right? Remember this? Remember sigma? Sigma means the total sum, add up the summation. So the total sum of line 1 is 4 plus 5 plus 5 equals 14. Okay, 14 here. Now let's see what happens for line 2. Line 2 has a predicted value for Dan. It has a predicted value for Billy. And it has a predicted value for Anna. Based upon this much education, line 2 thinks that Anna should be making this much money. But in reality, we just saw that based upon this much education, Anna is actually making this much money. Okay, so there's a gap there. Based upon this much education for Billy, line 2 thinks he should be down here. But in reality, Billy's around here. Okay, so Billy's doing all right there compared to what line 2 expects him to be doing. Okay, then finally, Dan, line 3, Dan has this much income. Line 2 thinks that Dan should be down here somewhere, but Dan is really all the way up here. Okay, so line 2 does not seem to be very good at predicting the amount of income that Dan, Anna, and Billy are making based upon their education levels. And this will matter. Let's take a look. Okay. Let's look at the distance, right? Remember, least squares principle tells the computer to choose the option of the line that minimizes the distance between the actual value of the y variable and the predicted value. So in other words, we are going to choose the line of best fit. We want the line that has the smallest distance. It has to have the smallest distance between the predicted value and the actual value of y. Okay, well here we have a predicted value for Dan. Okay, this is Dan's actual income level. This is the actual, this is the predicted. We could call this 15 units, 15 spaces. For Billy, this is the predicted value of Billy for line 2. Okay. Here is Billy's actual, okay, his actual income level. So let's call that, I don't know, 5 units. Finally, we have Anna, right? Anna, this is her predicted value for line 2. This is her actual value for line 2. Let's call that 10. Okay. So let's add up the total sum for line 2. Okay. The total sum for line 2 could be 10 plus 5 plus 15. Which equals, I need a little more space there. 10 plus 5 plus 15, which that is 30. Okay? So in other words, the total amount of space between line 2 and the actual amount of income that Dan, Billy, and Anna are making, the total distance for line 2 is 30 spaces. The total amount of space between Dan, Billy, and Anna, the total space for line 1, right, between the actual and the predicted values of line 1, that total is only 14. So we want to choose the line that minimizes the distance between the actual and the predicted values of y. We want the line of best fit. We want the line that cuts through the data as best as possible. That's the line we're interested in. Okay. Well, that line is going to be line 1. Okay. The least squares principle is telling you that the line that best fits the data will be the one that minimizes the sum of squared difference between the actual and the predicted values of y. Okay? In other words, when you want to figure out what is the impact of this independent variable on a dependent variable, you go out, you get data, right? You get income and years of education for Dan, for Billy, for Anna, for whoever. And then when you want to find out the size and the direction of the impact that one has on the other, what you're going to do is you tell the computer, all right, do the least squares principle. Okay. And when it goes out and it actually runs the least squares principle, what the computer is doing is it is calculating what the line is. It's trying to figure out the line that minimizes the distance between the actual and the predicted values of y. In this very simple example, what we're doing is we have line 1, not line 2. Line 1 has a total of 14 spaces. It's only off by a total of 14. Line 2 is off by a total of 30. So therefore, line 1 has minimized, or it has cut through the data better than line 2. Therefore, we really like line 1. Line 1 is the least square principle. Okay, the square comes from here, from the squared. And then least is minimum. We're picking the least square. If we find the line that has the smallest discrepancy between the actual and the predicted values, then we have the line of best fit. Okay. If we have the line of best fit, I'm just going to erase a bunch of this now and draw a lot of it back. Okay. But if we have the line of best fit, right? Here's line 1. We have Anna. We have Billy. And we have Dan. Okay. These are the actuals. These are the predicteds, right? This is a y hat for Dan. This is a y hat for Billy. This is a y hat for Anna. right? Okay. This is Anna's predicted value. This is Billy's predicted income value. And this is Dan's predicted income value. Okay. If we have this line, well, guess what? Every single line, every linear line, lines are linear, right? Every line comes with two features. Every line comes with a slope. Let me write it to not confuse you. Every line comes with a slope, and every line comes with a y-intercept. Okay? Now, in linear regression, we call the intercept alpha, which is not the same thing as the level of significance alpha. It's different. Okay? Level of significance from hypothesis testing is alpha, but when it comes to linear regression, they also called it alpha. I don't like it, but it is what it is. Okay? And then the slope is beta. Okay? So every line has an alpha and a beta. Okay? So again, from the top, where are we going with this, right? Okay. Well, we're trying to find out the relationship between education and income. To find out education and income levels, we go out and we get data. We collect data on Anna, Billy, and Dan. We should have way more observations, but for just to explain this, we have 3. Okay. Once we have information on Anna, Billy, and Dan, now we can run something. We can run a computer program called linear regression, right? It's in Microsoft Excel. You can use, and it's in Google Sheets. You can run a regression. When you run a linear regression, you are doing something called the least squares principle. Okay, the least squares principle. The least squares principle, what it does, the least squares principle tries to minimize the distance between the actual values of y, the actual dependent variables values, and the predicted values of y, the predicted values of the dependent variable. That's what the least squares principle is doing. Okay? Now, when the least squares principle goes out and when it finds the line of best fit, right? When the least squares principle gives you the line of best fit, right? It says, okay, line 1, the total amount of error in line 1, the total error there is 14 units. The total error in line 2, which I erased, right? But the total error in line 2 is 30 units. Which one has less error? 14 units or 30 units? All right, well, 14. This is the one that has less error. So what's the line of best fit? It's line 1. Okay. Each line comes with a slope and a y-intercept. So line 1, by definition, this is line 1, it has a y-intercept and it has a slope. Okay. The y-intercept is going to be A. The slope is going to be beta, right? Alpha and beta. What do we do with those numbers? Well, because it'll actually be numbers, right? The y-intercept will be, I don't know, 10, and the slope will be 15, right? What do we do with those numbers? Well, we take those numbers and we plug it into our equation right here. We say, you know what? We say that income is equal to alpha plus beta education. Okay. So if we suppose that alpha equals 10 and beta equals 15, then we could write income equals 10 plus 15 education. Okay. Now, so therefore, what should you expect your income to be for a bachelor's degree? Okay, let's see for a bachelor's. Let's call it undergraduate. It's an undergraduate degree. Okay. Well, an undergraduate degree, you go to K to 12, right? K to 12, you go to high school, and then you get another 4 years of education after that for undergraduate, right? So K to 12, and then you get another 4 years. So we'll call that 16 years of education for an undergraduate. So we could assume that if you, just according to this model, which is a little, ridiculous, right? But we could say that you could expect to make $250,000, right? If this is the correct model, right? If 10 was our alpha and beta was our 15. Where did I get that from? Well, I got it from right here, right? Let's just pretend that the slope of this line is 15, and let's pretend that the y-intercept is 10. Okay? If the y-intercept was 10 and the slope was 15, then we could say then we would write income is equal to 10 plus 15 education, which means that if you get an undergraduate degree, that's 16 years of education. 15 times 16 is 240. 240 plus 10 is 250,000. So we would say, all right, with an undergraduate degree, we would expect somebody to make $250,000 a year. Now, obviously, this is off, right? Uh, I'm just trying to highlight what a linear regression does, but that's what you would do. You could plug numbers in and actually estimate a value for the dependent variable. So let's say that you were thinking about going back to college, and you were thinking about getting a master's degree, right? Master's degrees usually take 2 years, okay? So usually, right? So that would jump years of education. Your education would go from 16 to 18. Okay. So what would you predict your income to be now? Well, with a master's degree, you would predict your income to be 15 times 18, which is 270 plus 10. You would expect it to be $280,000 per year with a master's degree. Okay. So that is what we do with linear regression. Okay. Linear regression, it's the ongoing process. It's the ongoing process of establishing the size and the direction. Okay. This is the size right here. The size is this 15. It's also the direction. It's the size and direction of a causal relationship between an independent variable and a dependent variable, right? Education is an independent variable. You can decide Okay, I want to go to college, right? I want to go to graduate school. I want to get a doctorate, whatever. You can decide. That's independent. But based upon that independent decision, that will change your income, right? Income depends on your years of education. Well, what's this process? How do we actually establish the size and the direction? The way we establish the size and direction is through the least squares principle. The least squares principle, we say like, hey, I want to know the size and direction of the relationship between an independent and a dependent variable. So what I do is I collect data on individuals or on whatever it is I'm studying. I go into Microsoft Excel, I go into Google Sheets, and I say, run a linear regression, right? All you have to do is go to data analysis, regression, just run a linear regression. When you click enter, the computer will begin performing the least squares principle for you. What it will do, the computer will actually calculate the line of best fit. The computer will find the line of all your data points, right? Of all your data points, it will calculate the line of best fit. It will calculate a line that minimizes the distance between actual values and predicted values, right? Between actual values of the y variable, between the actual values and the predicted values of the y variable. Okay? It will find this gap. It'll find the gap between the actual and the predicted values of y. Okay? When it does that, when it actually calculates the distance, the minimal distance between the actual and the predicted values of y, when it calculates that minimum distance, that line, what I called line 1 here, right? That line will have a slope, which is b, beta, and that line will have a y-intercept, which is alpha. Those two numbers, which I made up as 10 and 15, those two numbers will actually, you can plug them right into an equation. You plug those numbers right into a linear regression equation where you have alpha and beta. Alpha, I made 10, beta, I made 15. And once you have an intercept and a beta, which is known as the regression coefficient, beta is the regression coefficient. But once you have alpha and beta, right, the intercept and the regression coefficient, you can begin to start estimating the relationship, or this, you can start to estimate the impact that an independent variable has on a dependent variable. So you can start to estimate, you know what, with a master's degree, I think that my income with a master's degree, I think my income is going to go up to $280,000 a year. And then you decide whether, you should get a master's degree or not. Or you start thinking about whatever it is you're looking at, you start making operational decisions based upon your linear regression. Okay. So what we really care about here, we really care about these betas. Okay. Beta is the regression coefficient. Okay. Beta is the regression coefficient. That means that beta is exactly what tells us the size and the direction of the causal relationship. Beta is what we're after. Beta is the regression coefficient. The regression coefficient is what tells us the size and the direction of our causal relationship. Okay. So in other words, when the least squares principle gives us the line of best fit, the line of best fit is beta. That's what we're after. And therefore, if that's what we're after the line of best fit, right? We get the line of best fit. We get the line that has the minimum sum of squared distances. We get the line of best fit. That line has an alpha and it has a beta. It has a y-intercept and it has a slope. The slope is beta. Beta is the regression coefficient. And the regression coefficient is what tells us the size and the direction of the relationship between the independent and the dependent variables. Okay. So therefore, our regression coefficients are betas. That's what the whole process of linear regression is based around. Okay. What we're trying to do is get an estimate of beta so that we can then forecast the value of a dependent variable. Okay. All right. That's an introduction to linear regression. That's a very, very basic introduction. I was trying to keep it not too long. I don't want to go crazy into linear regression, right? Because as I mentioned at the top, it's really its own class, right? Linear regression, if you find this interesting, I hope you do, linear regression is really econometrics, okay? I just wanted you to have a basic exposure to what linear regression is so that you could judge whether you like it or not. I would encourage all of you to take econometrics or at least become somewhat familiar with the concept, even if you just do it on your own time. But it's very important to understand what linear regression is doing because that's how we make estimates of dependent variables based upon independent variables. Whenever you hear somebody say, oh, the forecasts were right or the forecasts were wrong or something, they're talking about linear regression. Okay. So, and specifically within those linear regressions, if their forecasts were right or wrong, what they're saying is they're talking about their regression coefficients. And then, just to finish the thought, right? Let's say that your forecasts were wrong. Well, that's okay. That's not the end of the world. Remember, linear regression is an ongoing process. If it's an ongoing process, if your forecasts weren't particularly good, guess what? Try to make them better. Try to make it better next time. Okay. On the other hand, right, if your estimates were very good, right, if the forecasts were right, okay, well, one, you could probably always make it better, but two, that doesn't mean that they'll be as good the next time around. So again, this is an ongoing process. In linear regression, you are always looking at your model. You're always evaluating it. You're always trying to reevaluate it, right? And see how you can improve it. Okay. So that's an introduction to linear regression. Again, if you find it interesting, I would encourage you to go on to econometrics. And again, that's how we make forecasts, things like that. But that will conclude this lesson now on correlation and linear regression.